Alright, so the final topic we're covering today is RC circuits, circuits that contain both a resistor and a capacitor in series. The reason this arrangement is interesting is because as the capacitor is charged or uncharged, the voltage, and therefore the current on the circuit, changes through time. This type of behavior of charging and discharging of a capacitor, producing alternating, increasing, and then decreasing current on a circuit, is useful to produce periodic flashing, such as car turn signals, flashing crosswalk lights, and other things. So, charging a capacitor. To understand the dynamics of what's going on in this time-varying circuit, we must first learn the function of that, the function that current follows through time as the capacitor charges and discharges. So say we have this circuit, of which I've kind of described, but with one additional thing in there. So we have some EMF source, right, this longer line being the positive, and that's connected to a resistor and then a capacitor, right? And then the last thing I'm going to add is a switch. This is how we would designate a switch. So if the switch is open, it looks like this. Switch is closed, then could look like that, or you could just draw a line. But open switch. So if that switch is open, that means the circuit is not a loop, right? It's not a circuit, and current isn't flowing. But as soon as you close that switch, then current can begin to flow, yeah? So there is an EMF source on the circuit, and once the switch is closed, current does indeed begin to flow. So let's go ahead and close that switch here. Oops. There we go. Every now and then OneNote decides that I don't need as much room down below at the bottom of the page that I actually do want, and it just collapses it on me. Alright, so once the switch is closed, then current, which I'm designating as this little lowercase I because it's going to be changing over time, and I just want a way to kind of designate that something new is happening here. So this EMF source here contributes to this current flow here. And I'll put some points on here that we can perhaps talk about, although I'm not sure that we need to. But as this current begins to flow, this resistor and this capacitor act in such a way that positive charges accumulate on one plate of the capacitor and negative charges, I'll use blue, negative charges accumulate on the other. And that's just simply because positive charges are being pushed along this way, right, quote-unquote rolling downhill, right, and you can equivalently think of negative charges as moving this way, or you can think of positive charges that were on the plate as it was neutral, an equal amount of positive and negatives, are moving this way off of the plate, leaving it with a deficit of positive charge and therefore a buildup of negative charge, right? We'll keep thinking in terms of this positive charge moving because that's how we define current, but it's also important to remember that it is the electrons that are moving in the end, right? So it all actually is the reverse, but because of the way that we define current, we'll keep talking about everything in terms of positive charge. Alright, so what amount of current flows? Well, it's given by Ohm's law. So we have the initial amount of current at moment 0, right when that switch is closed, is equal to V, we'll say, let's see, well, we'll say this is VAB. Let's just say this is V. Alright, there we go. I think my notes need correcting. V over R, which is EMF over R, right? In fact, that's what we'll do. We'll just skip right to this one, right? And we're treating this like the voltage source, and so that's just V equals IR from Ohm's law, right? So that is the amount of current that flows initially. But notice that as these charges build up, as they do on the capacitor, right, you have this interesting situation where the capacitor, as it charges over time, it actually begins to resist resist is probably not the right word to use. It begins to repel new positive charges moving down the hill, down the circuit, towards itself, right? And so as positive Q increases to big positive Q, and then you have big negative Q on the other side, it's resisting and it's repelling the positive charges from coming down the circuit, right? Because there's a separation. They don't continue on across. They stop right there and build up on the plate. Oops. I drew this arrow. Now let's see if I can get it back. There. So, this means that as the capacitor charges up and it's supplying a potential difference or voltage to the circuit, the capacitor's voltage is in competition with the EMF source that's charging it. And so thus we need to think about the net voltage on the circuit. So there's some positive voltage here. We can just call this 18 volts or something. And as the capacitor charges, after a few seconds, maybe it's going to be a negative 2 volts, right? Negative because it wants charges to move from its positive to its negative this way. But that is in competition with the EMF source, which wants charges to move from its positive to its negative, which will be counterclockwise here. So they're in competition, these two voltage sources. The EMF source, you can think of it as a battery, and the capacitor as it's charging up, right? And so the net voltage would be the positive 18 volts minus, at that moment, 2 volts, if that's how charged the capacitor is. And so the net voltage in that moment would be 16 volts. And you wait 30 more seconds or so, and maybe this capacitor is charged up to a negative 16 volts. And so then the net voltage would be a positive 18 from the original EMF source, minus 16 volts, which would be a positive 2 volts, right? So far less. And so as this net voltage changes, right, we'll say this net voltage, and now this is the current at some time t, I guess, you have this current changing each time, right? The resistance isn't changing. It's the same resistor on the circuit, but the net voltage is changing, and so the current is changing, right? And as it charges, it's decreasing proportionately to this net voltage change. And indeed it does. It follows this inverse exponential function here. So if you have current on one axis, I think I have nice axes I can use. There we go. If you have current here, you have time here, then it follows some function like this, right? Where this is the initial current, and over time it drops with the inverse exponential. And it's this function here that defines it. So the initial current times e to the negative t over RC, right? So this is all raised to that power. And this quantity RC is the resistance times the capacitance. So it would be the resistance in ohms times the capacitance of the capacitor in farads. And that's often referred to as the time constant. Right? Time constant. And that is the Greek letter tau. And so that is RC. It's also called the relaxation time of the circuit. And the reason that it's a time quantity is because if you take ohms for R times farads for capacitance, then you get, for capacitance, then you get V over A is ohms times C over V is farads. It's coulombs over volts, right? It's equal to C over A, right? Because the V's cancel, which is, amps is coulombs per second, so that's coulomb seconds per coulombs. Coulombs cancel, and so you're left with seconds. And so it is indeed a time quantity, this R times C, and so it's oftentimes called the time constant of the circuit. All right, so now for discharging. So let's go back to our same thing. I'm going to lasso this guy. Let's see if we can do this. Don't need you. Copy. Paste. All right, so now discharging. In order to discharge a capacitor, what you need to do is to remove the original EMF source that charged it, or you have to remove the competing voltage source, right? And so when this thing is fully charged, the way that we know that it is fully charged is that the voltage of the capacitor, we were saying it was 18. So if there's 18 volts of the EMF that's charging it, say battery that's charging it, then there's no net current, right, when the net voltage is equal to 0. So positive 18, right? So positive 18 volts minus, now the capacitor is fully charged to negative 18 volts. So that's 0 volts, and so V equals IR, right? I equals V over R. And if V is 0, then I is 0, and there's no charge moving, and so there's no more accumulation of charge on its plates. So it has no physical way to keep charging because the battery has, so to speak, been all it can be. It has supplied as much voltage, pushing enough current as it can to charge this capacitor, right? Much like a spring, it's like compressing a spring, and if you only have so much force and it gets harder and harder to compress it as time goes on, as the more you press, then a constant force will only compress a spring so much until it's fully compressed, right? So it's the same concept here. Okay, so given the fact that it's now fully charged, the way that we would discharge it is to remove this competition of voltage. So the capacitor has this negative 18 volts, which is telling charges, it wants charges to move from its positive to its negative. That's the current that it would have if it were king of the world. And then this EMF source, this battery that charged it, wants charges to move in the opposite way. And so if we just remove this EMF source, right? And I'll get rid of all these guys. We remove the EMF source. Well, now the capacitor is king of the world. It can have charges move clockwise, around the circuit from its positive to its negative, according to its charge of negative 18 volts. The negative is simply because we were defining this way to be negative, because originally we were defining this way to be positive. It's just a convention that we made up on the spot, right? You could flip. It's whatever you want it to be. All right. And so what happens is these charges that have built up over time, they diminish, right? Because they're physical piles of charges, you can think of them as, built up on the plate, right? And so over time, instead of big Q, you have little q, just a little bit of charge left, and just a little bit of negative charge on the other plate, right? And so after some amount of time, you have the capacitor charged less. It is discharged from its original fully charged negative 18 volts to now maybe it's like negative 6 volts, and then you wait another 30 seconds or so, and maybe it's negative 2 volts then, and eventually, theoretically, after infinite time, but eventually it's effectively fully discharged. No more charge will be pushed across around the circuit. All right, so what function does that follow? we have our same axes here. Let's see, I gotta go this way. There we go. And this is current again, and this is time. If this is our original current, it's negative because it was going the other way, right? So just like the voltage is negative for the capacitor, just because our convention, right, that we decided that this was going to be negative. So the current is negative at the start, and then it slowly decreases according to a inverse exponential function here, right? All right. And so what that looks like is I, as a function of t, is equal to I naught e negative t over the time constant RC, or tau. And that's the exact same thing, right? That's the exact same thing. Where did I write it? Yeah. So it's the exact same function that it follows, whether it's charging or discharging. Meaning that if you were to add a light bulb to this circuit and watch what that light bulb does as it charges and discharges, a light bulb lights up brighter the more current that's flowing through it. And so that means that as soon as you started discharging the capacitor, right, you took out that voltage source that charged it, and you connected the wires back together, I'm next to a noisy street, sorry guys, then the bulb would light up as bright as it was ever going to, and then it would slowly start decreasing according to this function here, until it dims and goes out. And that would be the exact same thing you would see whether it's charging or discharging. So if you only had a bulb as an indicator, a bulb on the circuit as an indicator of whether the capacitor is charging or discharging, you would not be able to tell whether it's charging or discharging. Alright, so believe it or not, that ends our entire electric portion of this whole class. I mean, we're still going to call back to it and concepts and such, but next we move on to magnetic phenomena. And there's plenty of cool stuff to talk about relevant to circuits, so we're not leaving circuits behind, but we move on to magnetic phenomena next.